Welcome to this TrendGuards Explainer. Today, we're diving straight into two massive, verified quantum milestones that both dropped in a single week. Our mission here is accuracy above all else, so we're going to look strictly at what has been confirmed, exactly how we know it, and what it actually means for the future of global tech. All right, so as reported and fully peer-reviewed in Physical Review Letters and Nature, we literally just witnessed a massive double leap in both networking and computing. Researchers at the University of Science and Technology of China achieved a 420-kilometer quantum network entanglement, totally shattering previous records. And at the exact same time, Quantinuum officially confirmed their Helios machine as the largest trapped ion quantum computer built to date, running with 98 physical qubits.
To really grasp why this new network milestone is such a huge deal, we have to talk about the physics that's been standing in our way for 3 decades. You see, unlike the regular internet you're using right now, quantum signals can't just be easily amplified. And that is all down to a fundamental law called the no-cloning theorem. Basically, it means it's physically impossible to make a perfect copy of an unknown quantum state. It's a pretty wild quirk of nature. The exact second you try to measure or boost a photon carrying a quantum bit, boom, you collapse its state entirely. The information is just instantly destroyed.
So, as you can imagine, this creates a massive engineering headache. In our everyday classical networks, if a signal gets weak, we just slap an amplifier on the line every 80 kilometers or so, right? But in a quantum network, because of that no-cloning theorem, every single kilometer of fiber optic cable equals an exponential loss of those vital photons. The fiber just absorbs and scatters the light. You absolutely cannot just shine a photon farther down a pipe and hope for the best. We needed a fundamentally different architecture to cross vast distances. The team at the University of Science and Technology of China shattered the old distance record by more than 4 times. How? Well, instead of trying to force one single photon to survive that brutal 420-kilometer trek, they used atomic ensemble quantum memories. Think of these as little clouds of cold atoms. Using what's known as the DLZ protocol, memories at both ends spit out a photon that is entangled with its own atomic state. Those photons then travel only half the distance, 210 kilometers each, to meet up at a central station. And that is where a joint measurement performs something called entanglement swapping. Basically, these two distant memories that have literally never interacted directly with each other are now entangled. They bypass direct transmission completely.
And the crucial takeaway here? It's all in the math. The researchers confirm that once you get past roughly 320 kilometers, this memory-based approach officially beats out just trying to send photons directly. That 320-kilometer mark is the exact crossover point engineers have been chasing. It basically takes the quantum internet from being a theoretical physics experiment and officially turns it into a practical engineering roadmap. Now, at the exact same time, on the computing side of things, Quantinuum announced their Helios machine, and Nature verified this as the largest trapped ion quantum computer ever built. But look, while 98 physical qubits is definitely impressive, that's not the real headline. The real headline here is its 99.9975% single qubit fidelity. Why does that specific number matter so much? Because frankly, having a quantum computer with a million noisy, error-prone qubits is completely useless if the machine introduces errors faster than you can fix them. This incredibly high fidelity metric proves that error-resilient trapped ions can actually scale up without losing their quality. So how exactly are they pulling this off? They use a quantum charge-coupled device, or QCCD architecture. The mechanics here are just fascinating. The system physically shuttles perfectly identical atomic ions between 8 different trap zones. Because they can actually physically move any qubit to sit right next to any other qubit, Helios achieves what we call all-to-all connectivity. This dramatically reduces the circuit depth you need to run complex algorithms, which gives it a massive, massive edge over traditional static grid setups. To really grasp the broader industry context here, we have to look at the hardware landscape. Clear divisions are starting to pop up. Superconducting chips, which are the ones favored by giants like Google and IBM, are super fast, but they really struggle with noise and limited connectivity. Then you have neutral atoms, kind of the dark horse, improving steadily. But take trapped ion, for example. Quantinuum's Helios proves that this trapped ion architecture can actually compete in scale, while totally crushing superconducting chips in that vital metric of extremely high fidelity and all-to-all connectivity. They are proving that focusing on quality per qubit is a very real, viable path to fault tolerance. And zooming out geopolitically, we're seeing a really fascinating split in the technology stock. China is heavily leading the infrastructure of the network layer.
I mean, they're already operating the world's longest quantum communication backbone, and this new 420-kilometer memory link just cements their lead in routing. Meanwhile, the West is pushing the absolute limits of the compute layer, really prioritizing these high-fidelity machines like Helios. Honestly, whoever manages to seamlessly integrate both of these layers together first is probably going to dictate the entire quantum infrastructure of the 2030s.
So, what do these two confirmed engineering milestones actually mean for us? Let's ground this in reality. These advancements lay the verifiable groundwork for three major sectors. First up, cybersecurity. That 420-kilometer link means metropolitan-scale, physics-backed, literally unhackable networks are becoming realistic right now. It really accelerates the need for post-quantum migration today. Second, finance. High-fidelity, fully connected machines like Helios are exactly what financial institutions need to handle complex logistics and optimization workloads in the near term. And finally, pharma and materials. Having these error-resilient qubits is an absolute prerequisite if we ever want to accurately simulate molecules for designing new drugs and advanced materials. The quantum era isn't just coming soon anymore. It is actively being built right in front of us. So as we wrap up this explainer, I want to toss a question over to you. Which of these verified milestones do you believe is going to become a practical reality in our enterprise infrastructure first? Are we going to see that 420-kilometer quantum memory link take off, or is it going to be the high-fidelity 98-qubit Helios machine? Let us know what you think. Thanks so much for joining me for this authoritative breakdown. Stay curious, stay informed, and as always, verify your sources. Catch you next time.
Thanks for watching. Don't forget to like, subscribe, and share. It really helps the channel grow. See you in the next video.